Yeah, thanks. Yeah, no problem.
Hey everyone, and welcome to this week's PhySU Undergrad Colloquium. Today, Rami will be presenting about hydrogen diffusion and trapping in metals, a theoretical approach to embrittlement. Could we give a round of applause to our speaker? Awesome. You may start now.
Okay, thank you. Yeah, like you mentioned, my name is Rami Ayeche. I'm a second-year physics specialist here at U of T, and I'm presenting my project. I completed it this summer under Dr. Bilal Mansour at Texas A&M University. And yeah, let's get started. All right. So before I get started, I want to give a table of contents of everything I'll talk about. So first of all, what is hydrogen embrittlement? I'm going to answer that for you, and then talk about the real-world damage that occurs due to hydrogen embrittlement. And then also cover the factors that influence it. How does it occur? And I also talk about cathodic charging. That's also a method of studying hydrogen embrittlement. Um, and then I talked about modeling hydrogen diffusion trapping and detrapping, running the numerical model that I translate, and then talk about the results in the discussion. This is all going to make a lot of sense very soon. But first of all, what is hydrogen embrittlement? Well, hydrogen embrittlement is a critical problem in industries that need reliable, environmentally um, resistant metals. And intrinsically, metals absorb hydrogen, right? Hydrogen diffuses into metals. And what happens is what's called hydrogen embrittlement is that hydrogen accumulates near the surface of the metal and enters grain boundaries, dislocations, maybe some cracks. And all it does is propagates the cracks. It makes the cracks worse than they were before. It creates new cracks, essentially. And you can see the kind of damage that it does here, where this metal pipe has been essentially been deemed unusable because of damage due to excessive hydrogen presence. So this little diagram kind of gives you an idea of what it's like. So you have like, for example, here we have metal pipe, and then in an environment that is rich with hydrogen, essentially um, the hydrogen enters different cracks, different dislocations, grain boundaries, and makes the cracks worse, continues propagating those cracks, causing the metal to essentially crumble. It's embrittlement, essentially. So it's just, its ductility is affected and it does not perform as well in tensile tests. Now, the main concept behind why hydrogen embrittlement happens is mainly because of hydrogen trapping, where microstructural features that I mentioned, grain boundaries, dislocations, we also have vacancies and inclusions, all of these trap hydrogen atoms, leading to crack propagation. So we have two different types of traps within a metal. We have shallow traps, which or reversible ones, which allow hydrogen to escape pretty easily. Those are like grain boundaries. And then we also have deep or irreversible traps. These make hydrogen almost inescapable. The moment hydrogen diffuses into this trap, it cannot leave and will continue to do the damage that it does. That's the main thing with embrittlement, is that it's irreversible most of the time. And so trapped hydrogen contributes to embrittlement by creating localized stress concentrations in grain boundaries or dislocations. So certain points within the metal have a lot of stress, and hydrogen migrates to these high stress regions and does damage in the process. Now, what is that real world damage? So some of it, it mainly affects various industries, including aerospace. Like for example, when aircraft are flying through hydrogen dense environments, especially in the air, um, there are many in-flight failures that could occur um, due to hydrogen embrittlement occurring. So, and also in the energy section, pipelines, storage tanks, all of these could be storing hydrogen or even natural gas or anything. But this pipe right here was damaged as a result of hydrogen embrittlement. It was a pipe that was storing um, liquid hydrogen and it very quickly degraded and was no longer functional. Now, what about the factors that influence um, exactly how hydrogen embrittlement occurs? Right? Like I mentioned, compositional microstructural factors, so wide grain boundaries, dislocations, manufacturing defects as well, allow for hydrogen embrittlement to occur a lot more quickly. And then we also have concentrated points of stress where high strength alloys like aluminum, steel, titanium, um, All of these have high tensile strengths. So when you try to break them, it takes a lot of force to break these metals. And there are certain high stress, there are certain points within the metal that have a lot of stress. They're concentrated with stress. And the hydrogen atoms tend to migrate towards these high stress regions just because, for many reasons, but which don't cover the scope of this talk. But um, as you can see in this diagram here, this is another good representation where hydrogen atoms have gone through a crack, a manufacturing defect, and then this crack will continue to propagate until it gets worse. Now that we know what hydrogen embrittlement is, what exactly can we do to sort of study it? How do we know exactly how it works? And one method that's often used in laboratory experiments is cathodic charging. Now, cathodic charging, it's used so that we can introduce hydrogen into the metals quickly. And the way it functions is essentially we immerse metal specimen. So here, this would be a metal specimen. We immerse it inside a beaker of hydrochloric acid, and then we run it through a current. We go run it through a anode, a cathodic potential, essentially. So we apply the cathodic potential, and this causes the hydrogen within the hydrochloric acid to I guess, populate on the surface of the metal, which, if you can see the gas that's being released here, that's our indication that the metal is being charged, that hydrogen is diffusing into the metal, right? And as I said here, hydrogen atoms diffuse into the metal, leading to hydrogen trapping and eventual embrittlement. Now, this experimental technique, it's kind of set up like this. Like we have our power supply, we have our wires that are connected to the anodes and cathodes, and then we have the electrolyte hydrochloric acid and the metal alloy. And this whole setup, it essentially cuts down the amount of time it takes to induce embrittlement into a metal to around 24 hours compared to naturally it would take months or even weeks for embrittlement to occur. Now, even though this is a very useful tool we have, um, it still is very laborious. It's a very laborious task where we first need to acquire a metal sample. It's a very specific alloy that we're trying to study, and it would have to be put in this exact shape because later on we'd be putting it through a tensile test. So we would be testing the strength of the metal eventually. So it has to be shaped like this, and we have to clean and polish it. And that is a process that takes hours, sometimes days. And then we run it through, we put it through cathodic charging, and then even after cathodic charging, we have to clear the metal to prepare it for the SEM, the scanning electron microscope tests. And this process still takes a long time. It consumes a lot of resources. It consumes a lot of that amount of time can be cut down significantly because in my experience working in this lab and completing these experiments, many would fail. We would do all the polishing and there would be failures. So I considered how we can conserve those resources. How can we conserve the resources when we examine hydrogen embrittlement? And I guess the easiest answer is just simulations. It's kind of always been a default where if we look at the process of hydrogen embrittlement theoretically, we can be able to create numerical simulations to help predict hydrogen embrittlement under specific conditions. And we can also compare the susceptibility of the metal before the susceptibility of the metal to hydrogen embrittlement before we even validate it experimentally. So it will give us some ground just before we even begin any experiments. Because currently, a lot of experiments to do with cathodic charging have to do with a lot of the time we go into the experiments blind with no preconceived notion of what our results could look like. And so from now on, I'll just discuss the theoretical mechanisms of hydrogen embrittlement, and I'll explore the possible strategies we can use to model the process. So the mechanisms of hydrogen embrittlement, what we could do, one approach we could take is we could look atomically at the cause of hydrogen embrittlement, and there are many, many theories that cover this. And it does allow us to understand the intrinsic damage caused by hydrogen. But for our purposes, we will just be examining the net effect of hydrogen diffusion because we're more interested in the performance of the metal, less about its sort of atomic properties, right? So I'll be modeling the net effect of hydrogen diffusion on microstructural features without needing to capture the atomic level interactions. And this brings me to the model that I sort of developed around this idea. I call it, we could classify it as a phenomenological model. And a phenomenological model basically means that it has certain variables that you need to, certain variables are restricted to just values found from experimental evidence. So rather than being able to, I guess, solve these equations, certain variables that I'll be bringing up soon have to be found empirically. And this is kind of like the main structure of the model. So we have the total concentration in the system is the free hydrogen concentration plus the trapped hydrogen concentration. And this diagram sort of tells you all the free hydrogen is sort of located around the metal. This is still the cathodic charging experimental setup. So we have the electrode and the metal sample. And all of the trapped hydrogen concentration is within the metal. Now, fundamentally, first of all, we talked about how hydrogen embrittlement occurs due to excess hydrogen diffusion in the metal. So we can model this diffusion using Fick's laws of diffusion. And there's Fick's first law, Fick's second law, but we're more interested in the second law, where the variable B right there is one of the variables that I was talking about, which um, can only be filled in with a value that we find experimentally. It's all based on the microstructural features of the metal. It depends on the initial conditions. All of that would be found experimentally, but this covers the net effect. We are essentially updating the free hydrogen concentration across some measure of time according to this diffusion coefficient. And we're essentially observing the hydrogen concentration gradient of the metal. So we're seeing the distribution of hydrogen throughout the metal. Now, the second part, we talked about hydrogen trapping as well. Well, I simulated hydrogen trapping by essentially um, by using a kinetic model. I essentially uh, sort of, so we have this equation, C trapped. We're basically updating the concentration of trapped hydrogen according to the minimum between the trapping capacity or the maximum amount of hydrogen that can be trapped. And then we also have this relationship, K trap times C free. K trap is just simply a kinetic constant, which is also derived from experiments and helps guide how much um, how much of the free hydrogen is actually being trapped by the metal, right? And as you can see here, if the amount of trapped hydrogen reaches the trapping capacity, then no more hydrogen can be trapped. It reaches the capacity and it should be plateauing, right? And then finally, what we have to consider is also, I mentioned shallow and or reversible and irreversible traps. Well, we can consider that as well. We can also model that, where um, some of the reversible traps we can also model kinetically by updating the amount of the concentration of trapped hydrogen. So we take another kinetic constant, K release, but that would depend on temperature and stress. So let's say we applied a certain amount of temperature and a certain amount of stress to the metal after the cathodic charging experiment, after the hydrogen was trapped. What we would be doing is essentially sort of releasing some hydrogen and outgassing the hydrogen, and updating the amount of trapped hydrogen concentration within the metal. Now, this is the full model, essentially. These four equations sort of make up the backbone of the model. And I ended up taking these equations and translating them into um, a Python program to be able to kind of figure out the relationship between all of the equations and be able to sort of produce a couple graphs and whatnot. And the parameters such as the diffusion coefficient, the kinetic constants, they were all derived from literature, but they weren't used directly. They weren't used accurately to a situation with a specific kind of metal. It was more so I added in some very standard values just to kind of see if the distribution of concentration would be accurate. Now, before I show the results that the Python program produces, I want to sort of discuss the setup that I gave it. So let's take the same setup in the cathodic charging experiment. These are all my parameters. I gave it 100 spatial points. So for the ordinary differential equation, it would cover the entire thickness of the metal and across 10,000 time steps, each step 0.01 seconds. But essentially, within my program, I concentrated all of the stress to the center of the midpoint of the metal sample. So that essentially I could create a concentration profile that sort of well, it'll all make sense now. Where essentially near the middle, we're allowing the distribution to sort of accumulate near the middle and be able to see how it all distributes. But this is one result that I came to. As you can see, the red line is the total hydrogen concentration. Blue line is the amount of free hydrogen. And the orange line is how much is trapped within the metal. And as you can see, uh, the, the amount of hydrogen in the system, which is in the red line, aligns with how much with the sum of the trapped hydrogen concentration and free hydrogen concentration. So all of these align and essentially um, verify that the distribution is accurate and the equations are functioning as they are supposed to. And I wanted to play around a little bit with some of the values to see if certain restrictions that I put on the model were going to be translated. So what I did was I reduced the trapping capacity. I limited the trapping capacity to 0.005 atomic parts per million. And as you can see, it kind of plateaus at that amount. And I didn't discuss the green line, but the green line is just after outgassing, after detrapping the hydrogen. This is how much is remaining trapped within the um, the metal. And then what if instead of placing all the stress near the center, what if we placed it near the surface, right? Where which is usually the general case, but um, in here you can see that most of the hydrogen accumulates near the surface uh, with a very small thickness, and it consistently follows the same trends as last time. And if I limited the trapping capacity again, um, it would again plateau like how we want it to. And there are many different kinds of combinations um, of graphs that we can produce using just this model by tweaking the numbers around. We can get different phenomena. Um, yeah, there are different phenomena you can see, and as I showed, it produces relatively accurate results based on the parameters I give it, and the trends that my model produces often matches trends that were found in literature. Like for example, this distribution right here, uh, almost one-to-one matched a piece of literature, and and the model also has been tested to adapt to, has been tested enough where I can say that it is capable of adapting to different initial conditions, especially given the fact that it's phenomenological and all our data points or all our variables have to be confirmed with experimental evidence. So that makes it a very adaptable model for different metals and situations. And I mean, it's still a work in progress. I'm still developing it. My eventual goal is to um, turn it into some kind of universal platform for testing different kinds of metals, and possibly doing that. But yeah, it's a work in progress right now. Yeah, yeah. Thank you so much for listening. Yeah, and I wanted to thank my advisors that all helped me out throughout this project. Yeah, thank you. So let's give another that.
Mhm.